are some students who have not heard about the CPD. So they should take the class with Andre, because he's teaching about this. Okay, and then we look at some joint PMF tensor estimation methods and distinguish between marginal-based estimation, and there we look at two different criteria, and then data-based estimation, and again look at two different algorithms. Then we look at some simulation results, synthetic data experiments, and also real data experiments. And Joseph will also talk about a technique how we can speed up the convergence of the EM algorithm and present the so-called square EM algorithm. And finally, we will conclude. And then in the end, we show a picture from Jared's office. So the view from Jared's office will be the last slide that Joseph will show then. Is there a problem? Okay, so now let's look at the motivation. So estimating the probability mass function from partial observation of a discrete random vector is actually a core problem in statistical learning, because the knowledge of the joint PMF is considered as the gold standard. It enables optimal estimation under various criteria, such as the mean squared error and the minimum probability of error. Useful applications include, and they are not limited to these applications, of course, recommender systems. For example, for the recommendation of restaurants, recommendation of hotels, recommendation of movies, etc. By using the joint PMF of the ratings, we can predict missing ratings. For example, if we haven't watched one of the movies, or if we have not been to a particular restaurant yet, based on the conditional expectation of the available ratings, and then we can make recommendations based on these predictions. And another application would be data classification. For example, if we look at a biomedical signal processing application, the features could be the symptoms that a patient has, and then the labels would be whether a person has a certain disease or not. So using the joint PMF of the features and the labels, we then infer the label of a test sample according to the maximum a posteriori principle. These are just two applications that we can use once we have estimated the joint PMF. So usually, of course, the full PMF tensor is unknown, and it needs to be estimated from the data during a training stage. Estimating the joint PMF, however, via histograms is considered virtually impossible due to the curse of dimensionality. So the required amount of data grows, of course, exponentially with the number of random variables. For example, if we have 10 random variables with 10 distinct values each, 10 to the power of 10 parameters would have to be estimated, which is, of course, not possible. Or your PhD would take a really long time, right, if you have to do that when you're doing your PhD. So therefore, a histogram estimation is very inaccurate since there's a low probability of encountering any particular realization of our random variables. And as I said, a lot of data is required to obtain a reliable estimate, even more in the case of incomplete data. Incomplete data, as I mentioned, a certain person has not watched all the movies. Okay, let's consider a set of n random variables, capital X index n, and small n ranges from 1 to capital N, and each variable xn now has in discrete values. And then our aim is to estimate the joint probability mass function, that is the joint probability of x1 through x index capital N from partial realizations of the random variable. So how would we then, when we have done this, when we've achieved this goal, how would we use this joint PMF? So, for example, for data classification, right? Given a set of features, let's say x1 through xn minus 1, we want to compute the posterior probability and predict the label x index capital N using the map principle. So how can we do that? This would be the conditional probability of capital Xn being equal to In, given the values of the other capital N minus 1 random variables that we have observed. So we just take the joint probability of all capital N random variables and divide it by the joint probability of the known capital N minus 1 random variables. And this is obtained by summing over all possible values of I index capital N. right? So this I index capital N ranges from 1 to capital IN, of course. And this is called marginalization, okay? So, and then, of course, in data classification, we can look at all of these conditional probabilities for all possible values of IN, and then, for example, select the maximum. Or we could, in a recommender system, given a subset of ratings, x1 through xn minus 1, we can estimate xn using the conditional expectation. How is that done? So this would be the expected value of xn given the observed capital N minus 1 random variables. And now we just sum over all possibilities of this IN and weight the corresponding conditional probability that's computed according to equation 1 by the corresponding value of IN. Okay, and this is of course only useful if the IN are associated with some numerical values. It's not useful if this is blue or red, something like that, right? So this should be associated with some numerical values, like some ratings, for example, or some grades for students. Okay, so let's consider a very simple example. 4 movies, each with 5 possible ratings. Movie 1 would be Toy Story, then we have Shrek, we have Inception, and The Batman. And the joint PMF of a user's rating can be represented as a 5 by 5 by 5 by 5 tensor, X. So we have, because we have 5 possible ratings for all of these 4 movies. And for example, this would be one entry of the tensor, right? This is X of 1, 3, 4, 5. And this is the probability that a particular user rated Toy Story as 1. So it's a pretty bad movie. Shrek as 3, Inception as 4. And he liked The Batman best because he rated him, The Batman as 5. Okay, let's assume that this user has rated Toy Story, Inception, and The Batman, but has not watched Shrek yet. So what can we do? If we know the joint PMF, we can easily predict the user's rating for Shrek. How should we do that? We calculate the posterior probability vector R, which is 5-dimensional, because we have 5 possible ratings for Shrek. R of I, for I between 1 and 5, is then the probability of x2 being equal to I, given the ratings for the other 3 movies, right? So we have the joint PMF divided by this marginalized PMF. So we sum over all possible values of the second random variable from j equals 1 to 5. So we marginalize the second random variable in the denominator. And then we can calculate the MMSE estimate of the rating for Shrek by weighting, basically, these values Ri by the corresponding I and summing from 1 to 5. So based on the estimated rating, then, we can decide whether or not to recommend Shrek to this particular user. So it's very simple. Okay, now let's look at the naive Bayes model. Before that, let's look at the CPD. So the joint PMF, the probability of these n random variables, can be represented as an n-way tensor, capital X. So this tensor is real valued, of course, of size I1 by I2 up to IN, n-dimensional tensor, and each element of X is now the probability of a particular realization, the probability of a particular index combination, right? So the probability that Xi is equal to I1 up to Xn being equal to In. And X actually admits a rank R canonical polyadic decomposition. This is actually the tensor extension of the matrix SVD, in the sense that, we have the sum over capital R rank 1 tensors. And this would be the outer product of the rth column of all n factor matrices, An, weighted by the rth component of the loading vector, lambda. And we want to use, in the sequel, we want to use this familiar shorthand notation for the n-way CPD. So lambda is the loading vector, the ANs are the factor matrices, and the circle is the outer product. So the probability of a particular index combination is then given as this particular entry of the tensor, the entry I1 up to IN. And this is the formula from the previous slide for a particular entry of this tensor. And we can, of course, have a more compact formulation here by using the product of these factor matrices, of the capital N factor matrices. And let's illustrate this tensor for the case n equals 3. So for 3 random variables, here you can see we have the sum over R terms, and we take the corresponding entries, the outer product of the rth columns of the factor matrices an, and weighted by the rth component of the loading vector lambda. So this is here is R is equal 1, 2, up to capital R. Right? So this is the sum of these rank 1 tensors. Okay, in practice, random variables usually have some degree of dependence. That means they're not fully independent or fully dependent. So if they were fully independent, the joint PMF tensor corresponds actually to a rank 1 tensor, because then you can write it as the product of the marginals, right? So then this would be a rank 1 tensor. So a reasonable assumption is that the random variables are independent given another hidden latent random variable, let's call it H, that takes a finite set of capital R values. And this is known as the naive Bayes model. And this would be a picture of it. So these n random variables are independent given the state of this other hidden random variable H. For example, a rank 1 tensor we have in the United States, we have Democrats and Republicans, and given that this guy is a Democrat, we know what he thinks, right? And given that this guy is a Republican, we know what he thinks. Okay, so the probability of a particular realization according to this model is this joint probability. And here we have again the sum over the R values of our hidden random variable. This would be the probability of H being equal to R. And then we have the conditional probabilities, probability of x1 being equal to I1, given that H is equal to R, etc. Right? So again, we can write this as the product of these conditional probabilities. And of course, this looks like the CPD, right? The naive Bayes model looks like our CPD model. Here we have the two pictures, and we can of course identify the a priori probabilities of the random variables as the entries in our loading vector lambda, and then the conditional a posteriori probabilities. So the probability of xn being equal to I, and given the value of h being equal to r, as the entries of our factor matrices. Actually, right? So in would be the row index, r is the column index. Okay, so, and we have the so-called probability simplex constraints, which means that the lambdas, they're all greater than 0, and they sum up to 1. And the entries of our loading matrices an, they're all greater or equal than 0, and the columns also sum up to 1. Right? So these are called a probability simplex constraint. And this was actually introduced by Nikos Sideropoulos and his co-workers in this famous IEEE transactions on signal processing paper. So X admits a non-negative CPD, tensor decomposition. Okay, so the naive Bayes model leads to a nice Bayesian interpretation of the CPD. Let's consider again our earlier example with Toy Story, Shrek, Inception, and the Batman, and 5 possible ratings. And there are R equals 2, so the tensor rank would be R2 in this case, kinds of users. We have action movie lovers and animation movie lovers. And we might have this loading vector. So 40% of the population are action movie lovers, and 60% of the population are animation movie lovers. And then we would have, for example, these 4 factor matrices. Why 4? Because we have 4 movies. And we can immediately see that the columns of the factor matrices provide the probabilities of the ratings, given that a user is drawn from the action animation lovers population. So now I don't see my mouse anymore. Okay, here it is. Okay, and the action movies are actually Inception and the Batman. You can see the action movie lovers, they have higher ratings for these. Most of them actually rated Inception as 5, so 55%. And the Batman also has pretty good ratings from the action movie lovers, whereas the animation movie lovers, they prefer Toy Story and Shrek, and they have worse ratings for Inception and Batman in blue. Okay? So this gives us a very nice interpretation once we've estimated these parameters. Whereas if you use a neural network, you don't get these insights. Okay. So the implication is that any joint PMF admits a naive base representation with a finite latent alphabet, as shown by Nikos Zeropoulos and his co-workers in this paper. And the number of states R, the latent variable H can take, is bounded by, this would be the product of all dimensions except for one. This is a very loose bound, actually, for the rank. Uniqueness is not guaranteed with this bound. In addition, of course, the CPD uniqueness conditions must be fulfilled. And if you don't know about CPD uniqueness conditions, you should take Andre's course, because he will talk about the Kruskal conditions there, right? So, he will cover this. Okay, there are two main approaches for the estimation of the PMF tensor. The first one is marginal based, where we first estimate lower order marginals and then fit them to the CPD. And this was actually done in references 1 and 2. And then in reference 3, actually, we've introduced a database approach where we directly find the maximum likelihood estimate of the joint PMF using only the observed data without estimating marginals first. So we want to look at both approaches here. And for the marginal-based estimation, we look at two different cost functions, the least squares criterion and the Kullbach-Leibler divergence criterion. Let's start with least squares. And the full joint PMF can be recovered from marginals of order greater or equal than 3 under relatively mild conditions, as also pointed out by Nikos Zeropoulos. The idea is it's easier to obtain reliable estimates of lower order marginals than the whole tensor, of course. And lower order marginal distributions also admit a non-negative CPD. For example, let's look at the probability of n-1 random variables. You see that the ik is missing here. So we sum over all possible values of ik, so we marginalize it, and then express the joint probability in terms of the CPD. Here we have the loading vector, here we have the factor matrices, and then the dependence on the factor matrix AK can be eliminated by just summing from ik equals 1 to capital Ik, and you see we sum over one whole column, which is actually equal to 1 due to our probability simplex constraints. So now we get a non-negative CPD of the remaining n-1 random variables. So the order of the tensor has been reduced by 1. And we can, of course, continue this process until there are only 3 random variables left. Then we just have the third order marginals, and we have the corresponding factor matrices there, right? Of course, then we get a coupled tensor decomposition, as we see later on. So estimating the third order marginal PMF empirically, for example, by counting all co-occurrences of triplet combinations is then easier. Triplet combinations IKL, they range, of course, also from 1 to capital N, because we have n random variables. So the marginal PMF estimate, let's call it X index JKL hat, can be approximated by a CPD of order 3. So the corresponding factor matrices and this loading vector, which that of course only contains 3 components here. And the full joint PMF is obtained by solving a least squares coupled tensor factorization problem using AO-ADMM, as shown in reference 1. AO-ADMM is alternizing optimization based on the alternating direction method of multipliers. And this is the cost function that Nikos Zeropoulos has used here. So this would be the third order subtensor, our empirical estimates of these third order marginals, and they're actually fit to the corresponding parts of the n-dimensional CPD in the least square sense, right? And this is the third order CPD to fit the empirical estimates. And this is, of course, the cost function is the Frobenius norm squared of the difference. So it's a least squares cost function subject to our probability simplex constraints. Okay, so the least squares criterion that we had on the previous slide offers a relatively convenient optimization procedure and does not, however, it does not provide proper weighting. Why? Because it may attribute 0 probability to an element of the estimated PMF even when the empirical probability is non-zero. It's non-zero, but it has occurred, but it's very small, so it doesn't really it doesn't really matter if we use the least squares cost function, right? But this, from our application point of view, this is of course not good. Therefore, it's better to use the Kullback-Leibler divergence. It's a more suitable criterion in the context of PMF estimation, as we've shown in this USIPCO paper. It treats smaller empirical probabilities in a different way than larger ones, and it forbids a solution that attributes zero probability to an element of the estimated PMF where the empirical probability is non-zero. Okay, so the KLD, the Kullback-Leibler divergence between two PMF probability mass functions, x and y, these are tensors of the same dimension, three-dimensional tensors in this example, is defined as follows. This would be the sum over all indices. So this we have we index x logarithm y divided by x, and of course this is greater or equal than 0. This is always positive. Now let's expand this expression like this, and we get equality if and only if, of course, the tensor x is equal to the tensor y. And if x is fixed, actually, x is fixed. It corresponds to our empirical estimate. And note that the constant, so if x is fixed, minimizing 11, we want to minimize the Kullback-Leibler divergence between these two PMFs with respect to y amounts to minimizing this expression here. So c is a constant. It does not depend on y. Note that the logarithm of the probabilities are less or equal than 1. So this logarithm is less or equal than 0. A minus a negative number is positive. So we can just add the L1 norm here. And this is the element-wise product between x and logarithm y. So this is the Schur-Hadamard product. So it's a very convenient expression for the KLD that we want to use in the sequel. Thus, the following KLD-based coupled tensor factorization problem is posed. This is the minimization now. Here we have the empirical estimate of our third-order subtensor, and we minimize basically the KLD between the observed data and the parameterized model distribution here. This would be our third-order CPD that we want to fit to the empirical estimates, and subject, of course, again to the probability simplex constraint. And we have actually started this line of research with our USIPCO 2019 paper. So the non-convex problem is rewritten as two convex subproblems there, and then solved using reparameterization techniques. And the KLD criterion actually outperforms the least squares criterion with respect to estimating the true PMF, as we also see later in the simulations. Okay, now let's look at the second one, the second method, the database estimation. And using the observed data, the maximum likelihood estimate actually of the joint PMF tensor can be obtained, as we've shown in this signal processing letter paper. It is more efficient because we don't need to calculate marginals. And in the large sample limit, maximizing likelihood corresponds to the minimization of the KLD between the observed data and the parameterized model distribution. So let's consider a discrete random vector x again, where each xn is in the set from 1 to in. And y is also an n-dimensional random vector obtained as a partial observation of x, such that, and this is independent for each index small n, yn is equal to xn with probability 1 minus p, and yn is equal to 0 with probability p. So p would be our outage probability. It's the probability that we don't observe this particular entry. For example, we haven't watched that movie yet, right? So then we set this corresponding yn to 0. And the goal is to estimate the joint PMF tensor x from TIID observations of y. So we have some kind of outage probability. And also when Joseph talks about the movie lens data later on, then he has this outage probability. Okay, let small y be a realization of capital Y, and B be in the set from 0 to n, 0 because we might not, B from 0 to n is the number of non-zero elements in Y, and these have the indices n1 through nb. Then we can write the probability of Y like this expression, where this first factor Q is now the probability that Y occurs. And then B random variables are observed, so n minus B variables are not observed, and we express the joint probability of the B observed random variables in terms of their CPD here, the loading vector and the factor matrices. And then, of course, this is a more better a description of this product. And the factors corresponding to 0 unobserved elements are again marginalized out as discussed before. Okay, let's look at an example. For 4 random variables, this vector y should have the components 3, 4, 0, 2. So we only observe 3 random variables. We don't observe the third one. This is the probability here that y occurs, the q. And we want to marginalize over the random variable x3 that is not observed here. So we sum from I3 equals 1 to capital I3. And express this x tensor in terms of the joint PMF. And then, of course, we can sum over this the columns of A3. So this is 1. And we have the PMF of the CPD of the remaining 3 random variables. So this is the CPD in terms of the 3 factor matrices that correspond to the observed random variables. Okay, so now let's look at the log likelihood of y. So we take the logarithm here of this probability of y. C is just logarithm of q. It's just a constant that we don't consider further. And let's assume that we have capital T IID observations, y1, y2, up to yt. And then the joint log likelihood of these observations, ignoring constants, can be written like this. So this is the logarithm of the probability of these observations, y1 through yt. We just sum over these t observations. And then here, as this index, we now have nb of t here. And these are also the observed random variables. For example, the rating for a particular movie, right? So this is the equation. And then this is an optimization problem for the maximum likelihood estimation of our factor matrices, and our loading vector is just the, this is the log likelihood that we want to maximize. So if we take the minus sign of that cost function, we have to minimize it here, right? And subject again to our probability simplex constraints. So in reference 2, we've proposed a KLD-based alternating direction minimization procedure. This was the USIPCO paper. By rewriting the non-convex problem as 2 convex subproblems, so we minimize with respect to lambda and each an separately, and then solve these tasks using reparameterization techniques. And we've also proposed an EM-based algorithm, expectation maximization. You might know this from a different context, which arises due to the naive Bayes model implied by the low-rank assumption. So in many parameter estimation problems, actually, it's often the case that maximizing the likelihood is difficult or even intractable. So then it's usually possible to formulate an associated problem using an augmented data such that computing the maximum likelihood estimate becomes analytically and computationally easier. So here the complete data would be Z of t. It consists of the observed data Y of t and S of t. S of t is the unknown latent state. Right, so it's unobserved. And then the EM algorithm is a generic method for computing the maximum likelihood estimate of this incomplete data problem by formulating an associated complete data problem and then exploring the simplicity of the maximum likelihood estimate of the latter to compute the former. So in the first step, this would be the E step. We compute the conditional expectation of the complete data given the current observations and the parameters. So here, this is the expected value of the complete data, Z of 1 through Z of t, given the current observations, Y1 through Y of t, and the current parameters. This would be theta prime. So the first iteration, so denote lambda and all an at the first iteration as theta prime, and then we compute this. And we use this conditional expectation since we cannot compute the complete data log likelihood, since the latent state is, of course, unknown. these are some parameters that we can define. And actually, in the backup slides, we've defined them in terms of the parameters of the CPD that we have currently estimated, right? So they can be calculated in closed form. And then in the M step, we find the parameters that maximize this conditional expectation found in the E step and update our current parameters to this new parameter set. And then we get, so basically we maximize this conditional expectation and find the next theta. And we get a closed form solution for the new loading vector lambda and the elements of the factor matrices an. So in terms of the parameters that we've just computed before. And then of course we iterate. Okay. So we have one alternating directions algorithm where which is the optimal solution to an inner convex problem that's achievable. However, it's computationally expensive. And then we have an EM algorithm, which is computationally cheaper. So it has closed form updates, but however, it may converge slowly. So therefore, in reference 3, this was our USIPCO paper. This was the signal processing letter. We've had a hybrid ADEM algorithm where we run a few expensive AD iterations to get in the vicinity of the global optimum and then switch to the computationally cheaper EM for refinement. So this hybrid ADEM algorithm obtains more accurate PMF estimates than the original AO-ADMM algorithm proposed by Nikos Soropoulos based on triplets and the least squares criterion. So, however, we need some more insights into this hybrid ADEM algorithm. So to answer the following questions. So when exactly do we switch from AD to EM? Is it sufficient to run EM alone? How can we accelerate EM convergence? So Joseph will talk about that. How do the algorithms perform on real data? Joseph will also look at that. And we carried out some extensive simulation campaigns in 2 approaches. First for synthetic data experiments and then also for real data experiments, movie recommendations, actually using the movie lens dataset that's available on the internet. So let's look at some synthetic data experiments and compare the performance of the least squares criterion based on triplets and the KLD criterion based on ADEM. So ADEM, and we also compare, of course, the ADEM performance and the EM performance alone in terms of the convergence of the log likelihood. And for different parameter settings, the number of observations T is varied, capital T. The outage probability, small p, is varied. And we look at different initialization strategies. Okay, so we have 5 random variables, n is equal to 5. The alphabet size for all of them is 10, so in is 10. So we have a tensor of size 10 by 10 by 10 by 10 by 10, where we want to estimate the parameters, so it's quite difficult. The ground truth CPD components, they are generated from uniform distributions between 0 and 1, and then normalized. So, and then we get the observed data by taking into account our outage probability P. An and lambda are initialized randomly and normalized, and then the results are averaged over L equals 100 independent trials. And as a performance metrics, we use several performance metrics. Actually, one is the mean squared relative error between the true data PMF tensor and the estimated one. Average, of course, over our L trials. And then we also look at the Kullback-Leibler divergence between the estimated and the true PMF tensor, and the so-called factor match score that was introduced by Tamara Kolda and her group to basically look at the fit between 2 CPDs. The best fit would achieved if the FMS is equal to 1. Okay, so here comparing the least squares criterion versus KLD. This is in terms of the mean squared relative error, and on the right-hand side in terms of the Kullback-Leibler divergence as a function of the number of observations, T, on a logarithmic scale. And in yellow, we see the oracle maximum likelihood that assumes that the true latent states are known. So they provide, of course, a lower bound. And then we have the KLD-based estimation technique in red, and the least squares-based triplets in blue, and of course the ADEM algorithm performs better, especially if we have large values of T. And this is in terms of the FMS, the factor match score. as a function again of the observations, and also here the ADEM-based technique is significantly better than the one based on least squares on this marginal triplet approach. Okay, now we look at the switching. So ADEM compared to EM, and this is t is equal to 10 to the power 4, 20%, 25% outage probability. The rank is equal to 5 here. And this red point indicates the switch from AD to EM. And surprise, surprise, there's no difference, right? So here we don't use AD. Here we switch from AD to EM. Here we switch again. And this is as a function of the number of EM iterations. And yeah, convergence is actually achieved with EM alone. And this is also actually shown in the other simulations. Here we have the mean squared relative error as a function of the outage probability that's varied from 0.1 to 0.9. 0.9, we have only 10% of the data, and there's no difference, actually. Running EM alone is sufficient in terms of the mean squared relative error and the KLD. And then here we will have the FMS, also for the same scenario, and running EM alone is sufficient. Here we look at so as a function of t, again, the same outage probability, the mean squared relative error, and the KLD, and again, no difference between the different curves. And also here where we look at the FMS between the different curves. So I guess this would be the end of my part. Now we look at speeding up the convergence of EM. And Joseph, are there any questions so far? Maybe? If there are no questions, then okay, maybe then I should ask some questions because let's Joseph, yeah. Yeah, sure. Okay, then Joseph can show us how to speed up the convergence of EM.
Okay. So now we have seen a lot of the theory, and we've been introduced to the EM algorithm, expectation maximization. But one of the things that actually was said was that one of the issues that it has is that it sometimes converges very slowly. So I want to show you a technique for how we can achieve a faster convergence for EM. So so EM exhibits linear convergence, and actually, if you have like a data set with a lot of missing information, then this convergence will even be slower. Yeah. So we found one existing technique, which is called square EM. It is a technique that is used to accelerate the convergence of the steepest descent method. Yeah, and what we want to do is to adapt this approach to the PMF estimation context. Okay, and the main idea here is that we can approximate the EM iteration steps by a linear equation. And because of that, we can apply the square EM approach, since it's designed to solve a system of linear equations. Okay? Yeah, so we can also apply it to speed up EM convergence, and we want to adapt it. And so we adapt it, and then we have square EM PMF, yeah, which is another PMF estimation algorithm. Okay, so this is just a summary of the algorithm. So I'm sure you're all familiar with this this quadratic minimization problem. And usually what you do is that you take the gradient with respect to x, and you have a linear equation. Yeah, qx is equal to b. And on the EM side, yeah, you can represent one iteration of the EM algorithm as in the following manner. So we have the like the parameter vector here at the k plus 1 iteration, and this is just a mapping f that moves it from iteration k up to k plus 1. Yeah, and what we want to achieve is the optimal point, which is called the EM fixed point. Yeah, at which point, when we apply one more iteration of EM, we don't really change this solution. Yeah, and if we take a Taylor expansion about that optimal point, then we can see that we have this linear equation here, where the J is the Jacobian. Yeah, so it holds all the gradients of with respect to the optimal point. And so we can see that we have a linear equation here, right? And we have it also on this side. And in the classical case, of course, we can use the steepest descent approach in order to speed up, in order to solve this equation. And we have this update equation for the steepest descent, and we can write a similar update equation on the EM side. Yeah. Now that we've already approximated it by a linear equation. Okay, so we have a similar thing here. And we can also define an error equation between the current point and the optimal point. Yeah, so this is kind of how far we are from the optimal point. So we can just rewrite this update equation, and we have an error equation here. And we can do the same thing on the EM side as well. Yeah? So we can reformulate this update equation into an error equation. And then what is done for the steepest descent in order to accelerate convergence there is to apply the so-called CBB method. It's an existing approach. And the main thing to note here is that if you look at the two error equations, yeah, here, and what we have here, you see there's a kind of a squaring. If you compare this equation here and this one, you see that there's a squared here. And this is why this approach is called square EM. Yeah? It's like a squared approach. And this is the same thing that can also be done for EM, so that we have square EM. And if we square the error equation, we have this new error equation and the corresponding update equation. Okay, and so in our case, what we want to do is actually to use this error equation here, but the update equation. But remember that for the PMF, we need to guarantee that the loading vector and the factor matrices are all in this probability simplex. Yeah. So if we apply square EM as it is, we will not be guaranteed that we will meet these constraints. Okay. So what we need to do is we need to ensure that that the solution that we get is within these constraints. Yeah. So as we are saying here, for the PMF estimation problem, we should also fulfill the probability simplex constraints. And so that's what we want to do here. We want to adapt this procedure. Yeah. So I won't go through every step of this algorithm, but basically the parts that are not that are white or unshaded, these are what are there for the original algorithm, the square EM algorithm. And then what we propose was to add the parts in blue in order to ensure that the solution is a PMF. Yeah? And basically what is done here is for this update equation, we need to select a step size. So this step size is this alpha k. We need to select a step size that ensures that the solution is within these constraints. Yeah? So that is what happens in this blue part here. And basically, so these are pictures that show that if you look at this update equation, equation 3, you can see it's quadratic in alpha. So it would look something like this, yeah? And then basically what we need to ensure that the step size we select should be in this green part here, yeah? So that we ensure that the theta is always positive. So that's basically what happens there. And this is the summary of the square EM PMF algorithm, yeah, that we proposed. And so here we have the parameter vector that has all the factor matrices and the loading vector. And then what is done is you first run 2 EM updates, so 2 iterations of the EM algorithm. And then you do this linear approximation of the EM fixed point using the 2 solutions that we have from steps 3 and 4. And then we select our step size using the proposed adaptation procedure. And then we do a final EM update. And then after that, we can reconstruct our factor matrices and the loading vector. So one thing to note here is that we need 3 EM updates in this square EM PMF algorithm. So when we are comparing the 2 in the results, we need to ensure that that we have a fair comparison. Yeah. So these are the simulation results here. So we allow EM to have a maximum of 30,000 iterations. That's a maximum, and while square EM PMF is allowed only 10,000. Yeah, so that we have a fair comparison. And we compare it with the AD-EM algorithm that has already been presented, and the AO-ADMM, which is from the Sidiropoulos paper. Yeah. We have a 5-way tensor of size 10 by 10 by 10 by 10 by 10, outage probability of 0.25, and we have 10 to power 5 observations. Okay. Our metrics are the mean squared error between the current and the true parameter vectors, and the negative log likelihood as well. And we also have the CCDF, or as in this is the distribution of the runtime and the number of iterations. Okay? So let's look at these results here. So on the left, we have the mean squared error against the number of square EM PMF iterations. And you can see that if you look at the blue curve here, which corresponds to square EM PMF, we can see that it converges faster than EM alone, yeah, which is the green curve here. And also, of course, converges faster than the ADEM and the AO-ADMM as well. We can also, if we look at the negative log likelihood, we also see a similar thing here, yeah, in terms of convergence. But I think it's much clearer if we look at the runtime here. So this is the distribution of the runtime. This is the CCDF against the runtime, and the vertical lines are the mean values of the runtime on the left and the iterations on the right. So
maybe you should point out the least square space on the previous slide. The least square space, the dash line. The dash line doesn't converge.
Yes. This is important. So the black dashed line is the least is like the least squares approach that was based on the 3D marginals. Yeah, and actually here what happened was that we discovered that it required many more iterations in order to converge to the as in these solutions that we have here for square EM. So because of that, we omitted it from the other analysis. Yeah, so it would take very long to converge. And this is because it only looks at the marginals in the data, and if you have missing information, some of those as a three-dimensional marginals will not exist. So there's some inaccuracy there. While the EM algorithm and of course also the square EM, PMF, looks at all the data and does maximum likelihood. Yeah. Okay, so now we have the runtime, and you can see here that square EM PMF has a much faster runtime here if we compare it to EM and ADEM. Also, if we look at the number of iterations, yeah, you can see, and here, by the way, we have already adjusted for the fact that square EM requires 3 EM iterations. Yeah, so we can see also that we have much less iterations, and actually, if we look at the numbers, then square EM runs approximately 3.6 times faster than EM and has far fewer iterations. So this is indeed efficient PMF estimation algorithm.
So the horizontal lines or vertical lines, they actually do this, right? Yeah.
Yes, these are the mean values. Yes, yes. So now let's look at some real data before we conclude. So we are actually using the movie lens dataset. So this is a publicly available dataset with movie ratings, yeah, and the ratings are on a half-star scale from 0.5 up to 5. So what we do is that from the entire dataset, because it contains very many ratings, we choose only 10 of the top-rated movies from action, animation, and comedy. And then we map the ratings from the scale of 1 up to 10. Okay, so, and this is an example of how the the data set would look like. Yeah, so we have basically the users and the movies, and you can see there we have various. We have Toy Story, Star Trek, The Hobbit, all kinds of movies, and these are the ratings here. Yeah, and generally there are very many missing ratings there, so it's quite a challenging problem. And oh yes, I should also say in this data set, actually, the amount of missing data was 40%. So the P was equal to 0.4. Okay, so of course we do the usual training, validation, and testing. So we have the initial data set with 10 movies. And for each trial, we first shuffle the data set, and then we split it into these 3 training, validation, testing sets. In the training, for us, what we want to do is to estimate the PMF, or in other words, to estimate the CPD components of the PMF tensor. In validation, we want to select the best parameters. So in this case, it would be the rank. Remember, if you have a real data set, you do not know the true rank. Yeah? So you have to kind of select it by validation. But actually, in the next talk, we will show a way in which we can learn the rank also from the data. And then we retrain, and then we test. Yeah. So, and basically, the testing is we hide one rating from the observation, and then we predict it using the model. Yeah. So we've already talked about the 2 ways of estimation, the MMSE and the MAP. Yeah, we already spoke about this. And the metrics are the RMSE, between the true and estimated ratings, and the mean absolute error, yeah, between the 2 as well. So these are the results here. So we have AOADMM. This is the technique that uses the 3D marginals. Then we have the EM approach, and then we have square EM PMF, which is the faster one. Yeah. And we have some other techniques here that are just baselines. So what we can see here is that EM and square EM have a similar performance in terms of accuracy, but square EM has a much faster convergence, as we have shown. Yeah. So, and this basically demonstrates that that this algorithm is applicable also for real data as well. Yeah. So to conclude, maximum likelihood estimation of a low-rank PMF tensor is a more efficient way to do PMF estimation as opposed to using the marginals. The KLD criterion is superior to the least squares in the context of PMF estimation. We have shown that. We have shown that also we do not need this hybrid algorithm. We can run only the EM algorithm, and it's sufficient. And we also have presented an algorithm that speeds up the convergence of EM. Yeah. We have also shown some real data experiments. So thank you for your attention. This is the picture from Gerald's office, actually.